All right, let's get right into it. Today, we're going to crack the code on one of the most, and I mean most, famous interview questions out there, the two-sum problem. Now, it might seem kind of simple on the surface, but trust me, it teaches a really powerful way of thinking that you can apply to pretty much any challenge.
So let's just jump in with an example. Imagine I give you these numbers, 3, 5, 1, and 4, and I tell you the target is 6. Can you spot a pair in there that adds up to it? Go ahead, take a second. You got it right? It's 5 and 1. That super quick process your brain just did, that's exactly what we're going to teach a computer to do. But we're going to teach it to be as smart as possible about it.
But before we start writing any code or talking about fancy algorithms, we have to really, truly understand the mission. What are the exact rules of the game here? Getting this part right is basically half the battle.
Okay, so here's the official problem statement. We get a list of numbers, which, in programming we call an array, and we get a target number. Our job is to answer a really simple question, yes or no. Is there any pair of two different numbers in that list that adds up exactly to our target?
Now let's get into the nitty-gritty, the details that can trip people up. First, you can't use the same element twice. So if you have a 3 in the list and your target is 6, you can't just say, oh, 3 plus 3. Nope. Second, the order doesn't matter. 5 plus 1 is the same as 1 plus 5, and we have to be ready for anything. The list could have negative numbers, it could have duplicates, and at the end of the day, all we need is a simple yes or no. That's it.
So how do we even begin to solve this? Well, most of us, myself included, would probably start with the most direct, straightforward method you can think of. We call this the brute force approach, and honestly, it's a fantastic place to start.
The logic here is, well, exactly what it sounds like. We're just going to be super methodical. We'll take the very first number and we'll pair it up with every single other number in the list. Then we'll move to the second number and we'll pair it with every number that comes after it. We're literally going to check every single combination until we either find a match or we run out of pairs to check.
Let's walk through an example. Our list is 2, 7, 11, 15, and our target is 9. We start with the first number, 2. We pair it with the next one, 7. What's 2 plus 7? It's 9. Boom! We found it on our very first try. Problem solved, right? We can just go home.
Well, what if we weren't so lucky? What if the answer was buried at the very, very end of the list? Or worse, what if the list didn't have 4 numbers, but a million numbers? Checking every single one of those pairs would start to take a very, very long time.
And this brings us to the report card for our brute force method. On the one hand, in terms of memory, or what we call space, it's amazing. It uses no extra memory at all. But its time performance, that's what we call O of n squared. Now that's just a fancy way of saying that as the list gets bigger, the time it takes gets longer, way faster. If you double the list, the time it takes to solve gets 4 times longer. It gets slow, really slow. We can do better. We have to do better.
And that search for a better way brings us to the turning point, the big aha moment. This is where we stop just solving the problem and we start solving it elegantly and, more importantly, efficiently. So we've figured out the core issue, right? Trying out every single combination is just not going to work for big lists. It's like trying to find a specific house in a huge city by just driving down every single street one by one. No, we need a map. We need a smarter strategy. And this leads us to the crucial, game-changing question. We have to reframe the whole problem. Instead of taking 2 numbers and asking, hey, do you two add up to the target? We take just 1 number and ask a totally different question. What is the exact partner I need to hit the target?
And the math for that? It's ridiculously simple. The number we need is just the target minus whatever number we're currently looking at. This little formula, this is the key that unlocks the whole thing. It changes the problem from one of adding things up to one of just searching for something.
Okay, so how do we actually use this insight? Well, we build a much better solution using a clever tool called a hash set. The easiest way to think about it is it's like a magic box or a super fast checklist. It has one superpower. It can instantly tell you, have I seen this specific number before, without having to look through a whole list. So the new process is super simple. And best of all, we only have to go through our list once. For each number, we calculate its required partner using our magic formula. Then we just ask our scene box, hey, have you seen this partner before? If the box says yes, we're done. We found it. If it says no, we just add the number we're currently on to the box and move to the next one.
Let's walk through that same example. We start with the number 2. Our target is 9, so the partner we need is 7. We check our scene box. Is the number 7 in there? Nope, the box is totally empty right now.
Okay, no problem. So we just add our current number, 2, to the box so we can remember we've seen it.
All right, now we move to the next number in our list, 7. We calculate the partner we need. 9 minus 7 is 2. So we ask our box again, hey, have you seen the number 2 before? And this time, the box shouts back, yes, it's right here. And just like that, we stop. We're done. We've found our pair, and it was so much faster.
Let's look at the report card for this new method. The time is now O of n. All that means is if we double the list size, the time it takes pretty much just doubles too. We only have to make one single pass through the list. It is blazingly fast. Now what's the catch? Well, we use a little extra memory, that's the O of n space, to keep our scene box. But this idea of trading a little bit of memory to get a massive boost in speed, that's a fundamental concept in programming, and it is almost always a trade worth making.
But what if memory is super limited? What if you're told you absolutely cannot use any extra space? Well, there's another clever technique for that. Though it does have its own special requirements, it's called the two-pointer technique.
This method is your go-to move when you're in a situation where you can't use extra memory, and, this is important, you're allowed to mess with the order of the original array. It's a bit more of a niche tool, but it's a powerful one to have in your problem-solving toolkit.
Here's how it works. First, and this is the crucial first step, you have to sort the array. Then, you put one pointer at the very beginning, the smallest number, and another pointer at the very end, the largest. You add them up. In our example, 1 plus 15 is 16. That's too big, so we need a smaller sum, which means we move the right pointer in one step. Now we have 1 and 7. That's 8. Too small, so we need a bigger sum, and we move the left pointer in. Now we're at 2 and 7, which is 9. Found it? See how we just squeeze the pointers together to find the answer?
Phew. Okay, so we've looked at 3 totally different ways to solve the exact same problem. Let's bring it all together into one final actionable lesson that you can take with you.
This final scorecard really lays it all out. Brute force is slow, but it's simple. It's great for learning or for teeny tiny arrays. The hash set method is your champion. It's the best overall solution, trading that little bit of memory for a huge speed up. And the two-pointer method, which is a tad slower because of that sorting step, is your special tool for when memory is your absolute biggest concern.
So if you ever face this question in a real interview, here is your playbook for success. Step 1. Start by explaining the brute force solution. It shows you understand the core of the problem. Step 2. Then you level up. You blow them away with the optimal hash set solution, making sure to explain that key insight about looking for the needed number. And finally, Step 3. You mention the two-pointer method as an alternative, showing that you've thought about all the trade-offs, like space versus time.
And really, that's the true takeaway here. This was never just about the two-sum problem. It's about a whole new way of thinking. It's about learning to stop yourself from just diving in and instead ask, wait, let me reframe this. What information do I actually need to find the answer? So my final question to you is, with that powerful new way of thinking, what are you going to solve next?